Hello. The scene is the 1927 Solvay Conference held at the Solvay Institute in Brussels in October 1927, the site of the famous debates between Albert Einstein and Niels Bohr. The theme of the meeting is on electrons and photons. In the chair is Hendrik Anton Lorentz. The participants include Niels Bohr, Max Born, Leon Brillouin, Sir William Lawrence Bragg, Louis de Broglie, Arthur Holly Compton, Marie Curie, Peter Debye, Paul Adrian Maurice Dirac, Paul Ehrenfest, Albert Einstein, Sir Ralph Howard Fowler, Werner Heisenberg, Hendrik Antony Kramers, Irving Langmuir, Wolfgang Pauli, Max Planck, Erwin Schrödinger, and others. Here you see the photograph of the conference participants. So at the Born and Heisenberg, in their paper at the Congress, declared quantum mechanics leads to accurate results concerning average values but gives no information as to the details of an individual event. The determinism which has so far been regarded as the basis of the exact sciences has to be given up. A consistent interpretation of the quantum mechanical formalism is possible only on the assumption of a fundamental indeterminism. The real meaning of Planck's constant h, they declared, is this: it constitutes a universal gauge of the indeterminism inherent in the laws of nature owing to the wave-particle duality. Quantum mechanics is a complete theory. Its basic physical and mathematical hypotheses are not further susceptible of modifications. What was Einstein's reaction? He said, I look upon quantum mechanics with admiration and suspicion. Quantum mechanics might be a correct theory of statistical laws, but it is an insufficient conception of the individual elementary processes. And of course, his famous statement, God does not play dice. So the battle is joined. In one camp, we have Einstein, supported by de Broglie and Schrödinger, and in the other camp, we have Bohr, Heisenberg, and Born. The discussions would continue well after the formal presentations in the dining room and often well into the night. Every day, Einstein would come up with fresh objections to the statistical interpretation of quantum theory, and to support his objections, he would design elaborate thought experiments or Gedanken experiments. In the words of Otto Stern, Einstein came down to breakfast and expressed his misgivings about the new quantum theory. Every time he had invented some beautiful experiment from which one saw that the theory did not work. Bohr reflected on it with care, and in the evening at dinner we were all together and he cleared up the matter in detail. The debate between Bohr and Einstein resumed 3 years later during the 6th Solvay Congress in 1930. In a new Gedanken experiment, Einstein now considered a box filled with radiation and with a clockwork-operated shutter in one wall, so that a photon is released during an accurately determinable time interval delta t. By weighing the box before and after emission of the timed pulse of radiation, the energy of the radiation could be computed from the relation E equal to mc squared with arbitrarily small error delta E. After a sleepless night, Bohr showed the next morning that in accordance with general relativity, the effect of the gravitational field on the rate of the clock introduces precisely the uncertainty required by the Heisenberg relation. Louis de Broglie's pilot wave theory, presented at the 1927 Solvay Conference, was the first known example of a hidden variable theory. Here, the positions of the particles are considered to be hidden variables. The observer does not know the precise values of these variables. They cannot be known precisely because any measurement disturbs them. A collection of particles has an associated matter wave, which evolves according to the Schrödinger equation. In the pilot wave theory, each particle follows a deterministic trajectory which is guided by the wave function. Collectively, the density of the particles conforms to the magnitude of the wave function. De Broglie's pilot wave theory thus reinterprets quantum mechanics as a deterministic theory. Wolfgang Pauli raised the objection that the pilot wave theory did not deal properly with the case of inelastic scattering, and de Broglie's pilot wave approach was not discussed further at the meeting. Unable to find a response, de Broglie abandoned this approach until David Bohm's paper 25 years later reconverted him to the pilot wave approach. In the fourth chapter of his highly influential book Mathematische Begrundung der Quantenmechanik, published by Springer in 1932 and translated into English by Boyer as The Mathematical Foundations of Quantum Mechanics in 1955, John von Neumann considered whether the statistical theory of quantum mechanics constitutes a logically closed theory or whether it could be formulated as a deterministic theory by the introduction of hidden variables, that is, additional variables which, unlike other variables, are inaccessible to measurements and hence are not subject to the restrictions of the uncertainty relations. Von Neumann concluded that the present system of quantum mechanics would have to be objectively false in order for another description of the elementary particles than the statistical one to be possible. Von Neumann's proof was later shown to be flawed by Grete Hermann in 1935, but this went completely unnoticed by the physics community for over 50 years. Von Neumann devoted the last two chapters of his book to the problem of observation and measurement. He postulated that, in addition to the continuous causal propagation of the wave function governed by the Schrödinger equation at psi equals IH cross del psi by del t, which leads to psi at time t equals psi at time 0 times e to the power minus iet by h cross, the wave function undergoes, in the case of measurement, a discontinuous, non-causal, instantaneous change or collapse of the wave packet from the superposition state psi equals sigma n Cn psi n to an eigenstate psi k, whose eigenvalue lambda k is the result of the measurement. Thus, every quantum mechanical measurement involves an unanalyzable process, that is, no mechanism or theory is proposed as to how this collapse happens. This collapse of the wave packet is an unavoidable feature of any measurement process. So, to sketch the timeline of ideas and developments, we have de Broglie's matter waves in 1923, Born, Jordan and Heisenberg's matrix mechanics in 1925, Schrödinger's wave mechanics in 1926. These led to the 1927 Solvay Congress, where de Broglie presented his pilot wave hypothesis. Subsequently came the publication of von Neumann's book on the mathematical foundations of quantum mechanics and his proof that hidden variables cannot exist, which was found to be flawed by Grete Hermann in 1935, but as we showed, this was widely ignored. In 1935, Einstein, Podolsky and Rosen presented their paradox, which starkly brought out the weirdness of quantum mechanics. This was further emphasized by Schrödinger's hypothetical cat experiments. But in 1952, David Bohm actually constructed a hidden variable theory, although von Neumann had supposedly shown that such a theory cannot exist. But this was considered an alternative interpretation of the same theory, the hidden variable interpretation, as opposed to the statistical interpretation, also called the Copenhagen interpretation of Born, Heisenberg and Bohr. And this I call the shut up and calculate era, because the attitude of most physicists, especially in the United States, was that it was not possible to understand quantum mechanics, that it is not worth bothering about the philosophical implications or the interpretations of quantum mechanics, and the best thing that one can do is to just shut up and calculate what we can. In 1966, John Bell established inequalities which showed that hidden variable theories and the Copenhagen version of quantum mechanics gave different results that can be experimentally tested. And he also rediscovered Grete Hermann's proof. Between 1972 and 74, Clauser, Shimony, and Horn refined the Bell's proof and outlined practical experiments that could be performed in order to test these inequalities. In 1982 came the groundbreaking superluminal experiments of Alain Aspect in Paris, where he actually changed the setting of the detection apparatus between the time that the particles had interacted. So after the particles had interacted and before they were detected, he changed this setting of the detection apparatus. And he showed that the collapse of the wave function happens instantaneously, or at least it happens faster than a light signal can travel from one particle to the other. Okay. And these experiments were further refined by Anton Zeilinger between 1998 and 2005, which led to the developments in quantum cryptography and quantum computation, and all of these culminated in the 2002 Nobel Prize Award to Clauser, Aspect, and Zeilinger. And this I call the entanglement era. Even as early as December 1926, Einstein wrote to Max Born expressing his misgivings. He admitted that quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice. As is clear from the correspondence between Born and Einstein, Einstein's verdict came as a hard blow to Max Born, who valued Einstein's opinions. In the elections to the 577-seat Reichstag of the German Weimar Republic in September 1930, the Nazi Party dramatically increased its representation from 12 to 107 seats. Jews in Germany came increasingly under attack. Relativity was branded as Jewish science by German physicists like Philipp Lenard and Johannes Stark. This Deutsche Physik movement sought to discredit Einstein's work as a product of Jewish intellectualism and detached from the real world. In September, Einstein wrote a letter to the Royal Swedish Academy nominating Heisenberg and Schrödinger for the Nobel Prize. In December 1931, Einstein wrote in his travel diary en route to Pasadena, "Today I made my decision essentially to give up my Berlin position." In July 1932, the Nazis won 230 seats in the Reichstag. In December 1932, the Einsteins left Germany for good. As they closed up their house, Einstein told his wife Elsa, "Turn around, you will never see it again." He eventually settled at the newly created Institute for Advanced Study in Princeton, New Jersey. In January 1933, Hitler became Chancellor of Germany. With the passage of the so-called Law for the Restoration of the Professional Civil Service, most Jewish professors in Germany were dismissed from their positions. This included Max Born, who was suspended from his professorship at the University of Göttingen due to his Jewish heritage, although he was a Quaker by faith. He then emigrated to the United Kingdom. In their 1935 Physical Review paper, Albert Einstein, Boris Podolsky, and Nathaniel Rosen asked the question, can quantum mechanical description of physical reality be considered complete? And they concluded that the wave function does not provide a complete description of physical reality. Consider a particle of non-zero mass and a photon which have interacted at some time in the past. Without disturbing the heavy particle, its position or its momentum can be determined by measuring the corresponding property of the photon. For this reason, I feel inclined to ascribe physical reality to both these observables, said Einstein. The Einstein-Podolsky-Rosen paper contains the following definition. If, without in any way disturbing a system, we can predict with certainty, that is, with a probability equal to unity, the value of a physical quantity, then there exists an element of physical reality to this physical quantity. This assertion of physical reality hinges on the concept of separability, which is also called local reality or Einstein locality. As Einstein wrote to Leon Rosenfeld in 1933, what would you say of the following situation? Suppose two particles are set in motion towards each other with the same very large momentum, and they interact with each other for a very short time, after which they pass at known positions. Consider now an observer who gets hold of one of the particles far away from the region of interaction and measures its momentum. Then, from the conditions of the experiment, he will obviously be able to deduce the momentum of the other particle. If, however, he chooses to measure the position of the first particle, he will be able to tell where the other particle is. This is a perfectly correct and straightforward deduction from the principles of quantum mechanics. But is it not very paradoxical? How can the final state of the second particle be influenced by a measurement performed on the first, after all interaction has ceased between them? As Nathaniel Rosen wrote, there's this function psi describing a state in which the measurement of x1 would give x2 and the measurement of p1 would give p2, so that the measurements on one particle would give information about the other. Since the second particle was not being disturbed, it appeared that one could assign to it precise values of x and p, even though the formalism of quantum mechanics was not capable of describing such a situation. So we have two particles with positions and momenta x1 p1 and x2 p2 in a state of definite total momentum p1 plus p2 and relative distance x1 minus x2. This is possible because the total momentum p1 plus p2 and the relative distance x1 minus x2 commute. The particles are now allowed to interact. Observations are made on particle 1 long after the interaction has taken place. Measure P1 and we know P2 without having disturbed particle 2. Next, measure X1 and we know X2, again without having disturbed particle 2. But quantum mechanics tells us that P2 and X2 cannot be simultaneously known because their operators don't commute. Thus, Einstein, Podolsky, and Rosen concluded this simultaneous predictability makes the reality of P2 and X2 depend upon the process of measurement carried out on the first system, which does not disturb this first system in any way. No reasonable definition of reality could be expected to permit this. Bohr countered in his rebuttal that it is only the mutual exclusion of any two experimental procedures permitting the unambiguous definition of complementary physical quantities which provides room for new physical laws. He thus maintained that the Einstein-Podolsky-Rosen paper didn't call for any change in the interpretation of quantum mechanics. We shall now discuss a modification of the Einstein-Podolsky-Rosen paradox due to David Bohm. Consider a pair of electrons in the singlet state. The wave function of this singlet pair is given by 1 upon root 2 times alpha 1 beta 2 minus alpha 2 beta 1, the antisymmetrized linear combination of the product spin functions of the two electrons. Let the electrons now separate and fly apart. The electrons are still in the entangled superposition state singlet psi until we perform a measurement. Now we measure the spin of electron 1 along the z-axis. The result of this measurement has to be one of the two eigenvalues, plus half if it is in the alpha state or minus half if it is in the beta state. If electron 1 is in the alpha state, we immediately know that the spin of electron 2 is beta, and if electron 1 is in the beta state, we immediately know that the spin of electron 2 is alpha. Thus, until we performed the measurement, the system was in the superposition state, but as soon as we performed the measurement of the spin of electron 1, we immediately know the spin of electron 2 as either alpha or beta, not a superposition. And this collapse of the wave packet happens irrespective of how far the two electrons are. But according to special relativity, there is no physical signal which can go from electron 1 to electron 2 immediately. It can only go at or below the speed of light. That is the paradox. Okay. We shall return to this experimental setup in a later episode when we discuss Bell's theorem, which makes clear the difference between the statistical interpretation of quantum mechanics and any hidden variable interpretations, and it forms the basis of entanglement. In a measurement process, it is not just the system S, but the system S combined with the measuring apparatus M and ultimately with the observer that is the object of observation. According to von Neumann, the theory of the measurement is a statement concerning S plus M and should describe how the state of S is related to certain properties of the state of M, namely the positions of a certain pointer, since the observer reads these. Moreover, it is rather arbitrary whether or not one includes the observer in M and replaces the relation between the state S and the pointer positions in M by the relations of this state and the chemical changes in the observer's eye or even in his brain. Thus, according to von Neumann, it is not possible to formulate the laws of quantum mechanics in a complete and consistent way without a reference to human consciousness. Thus, we are not allowed to make statements like a physical quantity has a certain value. We can only say that an observer has made a certain subjective observation. According to Heisenberg, the laws of nature which we formulate mathematically in quantum theory deal no longer with the particles themselves, but with our knowledge of the elementary particles. This is made clear in the experiment of Schrödinger with his famous feline. In Schrödinger's diabolical Gedanken experiment, a cat is enclosed in a box with one atom of radioactive substance and a bottle of cyanide. The emitted photon can release the hammer to shatter the bottle and release the cyanide gas. Now wait one half-life. A half-life is a period during which half the amount of radioactive substance will decay. But since we have only one atom of the radioactive substance, that means that after one half-life we can say that there is 50% probability that the atom has decayed or not. Okay. Now open the box. What is the state of the cat? The answer is that until you open the box, the state of the cat was in a superposition state of 1 upon root 2 psi dead plus psi alive until you open the box. But as soon as you open the box, you know whether the cat is alive or dead. So after the box is opened, the cat is definitely either dead or alive. Okay. So who killed the cat? Was it Schrödinger, or was it you who opened the box and thereby knocked the cat from its superposition state into the alive state or the dead state? Okay. Eugene Wigner hit upon a really ingenious way to avoid this responsibility for killing the cat. Instead of opening the box himself, he had his friend open the box, but she doesn't tell him the result immediately. What is the state of the cat now? For Wigner, it is still in the superposition state, 1 upon root 2 psi dead plus psi alive, since he doesn't know. Okay. But for Wigner's friend, who has performed the measurement, for her the cat is definitely either dead or alive. So the state of the same cat is different for Wigner and for his friend. Now this is a very distasteful state of affairs for a physicist, because it means that statements in physics can differ from person to person. Okay? Now hidden variables are not the only way to avoid the collapse of the wave packet. There is also the many worlds interpretation of quantum mechanics, also known as multiverses, which I did not want to talk about since I don't consider it a scientific hypothesis. But I was asked to talk about it by some friends, so let me just mention it. In the many worlds interpretation of quantum mechanics, at a quantum event, at a quantum measurement, the system doesn't decide which of the eigenstates it is going to get knocked into, but it gets knocked into all of them, but just in different universes. It just so happens that in our universe, the system got knocked into this particular eigenstate. So in this way, we avoid the unpleasant collapse of the wave function, but at the cost of an infinite proliferation of universes at every quantum measurement. Okay, so every time you have let's say a screen which the electron will either pass through or get reflected, the universe splits. Now, if you want to believe that, go ahead. But I don't think it's a scientific hypothesis, because a scientific hypothesis needs to be testable. There should be some way that you can perform a test and be able to falsify a hypothesis. If a hypothesis is in principle not falsifiable, then it's not a scientific hypothesis. It's an article of faith. Okay, so we'll stop here.